Hi, my name is Hannah and this video is all about multiple linear regression. This is the third video in our playlist on regression analysis. Therefore, if you don't know what a regression analysis is or what a simple linear regression is, just take a look at the first two videos. If you like, you can find the content of this video in our book Statistics Made Easy. The link is in the video description. So let's start. What is a multiple linear regression? A multiple linear regression is a method for modeling relationships between variables. It makes it possible to infer or predict a variable based on other variables. An example. Let's say you want to find out what influences a person's salary. You take the highest level of education, the weekly working hours, and the age of a person. You now investigate whether these three variables have an influence on the salary of a person. If they do, you can predict a person's salary by taking the highest educational level, the weekly working hours, and a person's age. The variables we use for prediction are called independent variables. The variable we want to infer or predict is called the dependent variable. But what is the difference between a simple linear and a multiple linear regression? As we know from the previous video, in simple linear regression, we use just one independent variable to predict the dependent variable. For example, if we want to predict a person's salary, we use either if a person has studied or not, the weekly working hours, or the age of a person. Multiple linear regression, on the other hand, uses several independent variables to predict or infer the dependent variable. Therefore, the difference between a simple and a multiple linear regression is that in one case only one independent variable is used, and in the other case several. Both have in common that the dependent variable is metric. Metric variables are, for example, the salary of a person, the body size, or the electricity consumption. So unlike simple linear regression, multiple linear regression can include two or more independent variables. But what impact does that have on the regression equation? In the case of linear regression, this was our equation. We had one dependent variable y and one independent variable x. Now, in multiple linear regression, we have more than one independent variable. But don't worry, the coefficients b and a are interpreted similarly to those in a simple linear regression. If all independent variables are 0, the value a is obtained, so we get a value of a for the dependent variable y. Furthermore, if an independent variable increases by 1 unit, the associated coefficient b indicates the corresponding change in the dependent variable. Okay, let's make one small adjustment. Going forward, instead of y, we'll use y hat. But why? In the previous video, we learned that regression aims to model the dependent variable as accurately as possible. However, when working with real-world data, there's always some error. In other words, the true values often differ from the predictions. Now, y hat represents the predicted values from the regression model, while y denotes the observed actual values. Great, you're gradually becoming an expert. Now there are 4 topics to cover: the assumptions of regression, how to calculate a regression with data type, how to interpret the results, and finally, how to handle categorical variables in regression by creating dummy variables. Let's start with the first topic. So, what are the assumptions? The first 4 assumptions of multiple linear regression are similar to those of simple linear regression, but there is an additional 5th assumption. Let's briefly recap the first 4 assumptions and then we'll go into more details on the 5th assumption. Let's start with the first one, linear relationship. In the case of the simple linear regression, we were able to test this assumption easily. A straight line is drawn through the data. This straight line should represent all points as good as possible. If the relationship is nonlinear, the straight line cannot fulfill this requirement. In simple linear regression, we have one independent variable and one dependent variable, making it straightforward to plot the data points and the regression line. In contrast, multiple linear regression involves multiple independent variables, which complicates the visualization. However, you can still plot each independent variable separately against the dependent variable to gain an initial sense of whether a linear relationship might exist. Number 2, independence of errors. The errors, so the differences between actual and predicted values, should be independent of each other. This means that the error of one point doesn't affect another one. We can test this with the Durbin-Watson test. Number 3, homoscedasticity or equal variance of errors. If we plot the errors on the y-axis and the predicted values from the regression model on the x-axis, their spread should be roughly the same across all values of x. In other words, the variance of the error should remain constant. In this case, the assumption is fulfilled. But what about that case? Here we observe unequal variance. At low values of x, the errors are small, while at high values, the variance of the errors becomes much larger. Number 4, normally distributed errors. The errors should be normally distributed. We can test this with a QQ plot or with analytical tests. If you like, you can check out my video Test for Normal Distribution for a deeper dive. And what about the 5th assumption, no multicollinearity? First of all, what is multicollinearity in regression? Multicollinearity means that two or more independent variables are highly correlated with each other. As a result, the effect of individual variables cannot be clearly separated. Why is that a problem? Let's look at the regression equation again. We have here the dependent variable and there the independent variables with the respective coefficients. For example, if there is a high correlation between x1 and x2, or if these two variables are almost equal, then it is difficult to determine b1 and b2. If both are completely equal, the regression model cannot determine how large b1 and how large b2 should be. This means that one independent variable can be predicted from the others with a high degree of accuracy. An example: imagine you're trying to predict the price of a house. To do this, you use the size of the house, the number of rooms, and some other variables. Usually, the size of the house is related to the number of rooms. Large houses tend to have more rooms. So these two variables are correlated. If we now include both in our regression model, the model will struggle to decide how much of the price is influenced by size and how much is influenced by number of rooms. This is because they overlap in the information they provide, and this is multicollinearity. In this case, it becomes impossible to reliably determine the regression coefficients. If you just want to use the regression model for a prediction, the presence of multicollinearity is less critical. In this context, the focus is on how accurate the prediction is, rather than on understanding the influence of the individual variables. However, if the regression model is used to assess the influence of independent variables on the dependent variable, there should be no multicollinearity. Okay, but how do we detect multicollinearity? If we look at the regression equation again, we have the variable x1, x2, and up to variable xk. We now want to determine whether x1 is nearly identical to any other variable or a combination of the other variables. For this, we simply set up a new regression model. In this regression model, we take x1 as the new dependent variable and keep the others as independent variables. If we can predict x1 accurately using the other independent variables, x1 becomes unnecessary. Its information is already captured by the other variables. We can now do this for all other variables. So we estimate x1 by using the other independent variables, we estimate x2 by using the other variables, and we estimate xk by using the other independent variables. Okay, but what is a method to detect multicollinearity? For all k regression models, we calculate r squared, which is the so-called coefficient of determination. What is the coefficient of determination r squared? If x1 is the dependent variable and the other independent variables are used as predictors, r squared explains how well the independent variables explain the variability of the dependent variable. Therefore, a high r squared in this context suggests that x1 is highly correlated with the other independent variables. This is a sign of multicollinearity. Using r squared, we can calculate the tolerance and the variance inflation factor, short VIF. Basically, the VIF is 1 divided by the tolerance. If the tolerance is less than 0.1, it indicates potential multicollinearity and caution is required. On the other hand, a VIF value greater than 10 is a warning sign of multicollinearity, requiring further investigation. Typically, statistical programs like DataTab provide the tolerance and variance inflation factor VIF values for each independent variable. Okay, but how to address multicollinearity? There are two common ways to address multicollinearity. Number 1, remove one of the correlated variables. So choose the variable that is less significant and remove it. Or number 2, combine variables. Create a single variable by combining the correlated variables, e.g., taking an average. If you're using DataTab and calculate a regression, you just need to click on Test Assumptions. Here you can see the table with the tolerance and the VIF. Alright, let's work through an example on how to calculate a multiple linear regression and then look at how to interpret the results. Our goal is to analyze the influence of age, weight, and cholesterol level on blood pressure. So blood pressure is our dependent variable, while age, weight, and cholesterol level are our independent variables. To calculate the regression, we just go to datatab.net and copy our data into the table. If you like, you can load the sample dataset using the link in the video description. We want to calculate a regression, so we click on Regression. Now we simply click on blood pressure under dependent variable and age and weight and cholesterol level under independent variable. Afterwards, we automatically get the results of the regression. We will now discuss how to interpret the individual tables. If you need an interpretation of your individual data, you can just click on AI interpretation at each table and you will get a detailed explanation of your results. And if you want to test assumptions, just click here. But back to the results. Let's start with the most important table, the table with the regression coefficients, and then take a closer look at the model summary table. We will focus on these three columns. Here we can see the three independent variables, age, weight, and cholesterol. The first row represents the constant. So in our regression equation, let's replace x1, x2, and x3 with their corresponding names. So we want to predict blood pressure based on a person's age, weight, and cholesterol levels. Okay, in the first column, we see the unstandardized regression coefficients. These are our coefficients from the regression equation. Now we can calculate the blood pressure for a given person. Let's say a person is 55 years old, has a weight of 95 kg and a cholesterol level of 180. Then our model would predict a blood pressure of 91. So for example, if we look at the variable age, 0.26 means that for each additional year of age, the blood pressure increases by 0.26 units, assuming other variables remain constant. And what about the standardized coefficients? The standardized coefficient tells us the relative importance of each independent variable after standardizing the variables to the same scale. Why is this useful? Our model includes variables measured in different units, such as age in years, weight in kilograms. Comparing their unstandardized coefficients can be misleading because these coefficients are influenced by the units of measurement. For instance, if weight is measured in tons, the coefficient would be larger. If we measured in grams, it would be smaller. Additionally, the values for age in years are generally smaller than the values for cholesterol. So you cannot directly compare their unstandardized coefficients with each other. In contrast, the standardized coefficient remains consistent regardless of the units. This allows for direct comparison of the relative effects of different variables. For example, we can see that cholesterol level has the largest standardized coefficient, indicating that it has the strongest influence on blood pressure. In our video about simple linear regression, we explained the p-value in detail. The interpretation is similar in multiple linear regression. To summarize, the p-value shows whether the corresponding coefficient is significantly different from 0. In other words, it tells us if a variable has a real influence or if the result could just be due to chance. If the p-value is smaller than 0.05, it means the difference is significant. In our case, all p-values are smaller than 0.05, so all variables have a significant influence. Perfect! Let's move on to the next table, the model summary table. First, we get the multiple correlation coefficient R. R measures the correlation between the dependent variable and the combination of the independent variables. What does that mean? Here we have the equation for linear regression. Once the coefficients are determined, we can sum all up and calculate the predicted values y hat of the dependent variable. So if we use our example data, we have the real blood pressure data and we can predict the blood pressure data with the regression model. The multiple correlation coefficient R is now the correlation between the predicted values y hat and the actual values y. In other words, the multiple correlation coefficient R indicates the strength of the correlation between the actual dependent variable and its estimated values. Therefore, the greater the correlation, the better the regression model. In our case, an R value of 0.27 indicates a strong positive relationship. Okay, and what about R squared? R squared is called the coefficient of determination. R squared indicates the proportion of variance in the dependent variable that is explained by the independent variables. The greater the explained variance, the better the model's performance. For example, an R squared value of 1 would mean that the entire variation in blood pressure can be perfectly explained by the variables age, weight, and cholesterol level. However, in reality, this is rarely the case. An R squared of 0.52 means that 52% of the variation in blood pressure is explained by the model. What is the adjusted R squared? The adjusted R squared accounts for the number of independent variables in the model. This provides a more accurate measure of explanatory power. When a model includes many independent variables, the regular R squared can overestimate how well the model explains the data. In such cases, it is recommended to consider the adjusted R squared to avoid overestimation. Okay, and what about the standard error of the estimate? The standard error of the estimate measures the average distance between the observed data points and the regression line. A standard error of the estimate of 6.6 indicates that, on average, the model's predictions deviate from the actual values by 6.6 units. So if we predict a person's blood pressure using their age, weight, and cholesterol level, our prediction will, on average, deviate by 6.6 units from the person's actual blood pressure. Okay, if you want an interpretation of the other tables, simply click on AI interpretation. Earlier in this video, I mentioned that independent variables in regression analysis can be nominal. Okay, but what are nominal variables? Nominal variables are variables with different categories like gender with male and female or vehicle type. But how do we use nominal variables in a regression model as independent variables? Let's keep things simple. Let's start with variables with two categories. Imagine we have the variable gender with the categories male and female. Now we can code female as 0 and male as 1. The category coded with 0 is our so-called reference category. Alright, let's take a look at the regression equation. Suppose the variable x1 represents gender, then b1 is the regression coefficient for gender. But how do we interpret b1? We said 0 is female and 1 is male, so let's just insert this for x1. For a female individual, we have 0 multiplied by b1, and for a male individual, we have 1 multiplied by b1. Accordingly, b1 represents the difference between males and females. Now that we've discussed how to handle variables with two values, let's explore how to approach variables with more than two values. Let's say we want to predict the fuel consumption of a car based on its horsepower and vehicle type. To keep it simple, let's say there are only three vehicle types: sedan, sports car, and family van. Thus, we have a variable vehicle type with more than two categories. However, as we know in regression, we can only include variables with two categories. So what's the solution? This is where dummy variables come into play. Dummy variables are artificial variables that make it possible to handle variables with more than two categories. For the variable vehicle type, we create a total of three dummy variables: is sedan, is sports car, and is family van. Each of these dummy variables has only two possible values, 0 or 1. A value of 1 indicates the presence of the specific category, while a value of 0 indicates its absence. Instead of having one variable with three categories, we now have three variables with two categories each. These newly created dummy variables can be included in the regression model. Okay, but what does this mean for our data preparation? Initially, we have one column labeled vehicle type, where the individual vehicle types from our sample are listed. The first entry is sedan, the second is also sedan, the third is a sports car, and so on. From this column, we create three new variables. For the first vehicle, which is a sedan, we assign a 1 under the sedan and 0 under the others, as it's neither a sports car nor a family van. Similarly, the second vehicle is also a sedan. The third vehicle, however, is a sports car, so you assign a 1 under sports car and 0 under the others. By doing this, we've successfully created our dummy variables. One important thing to note: the number of dummy variables you create will always be the number of categories minus 1. So in our case, we have three categories, so we basically only need two dummy variables. Why is that the case? If we know a vehicle is a sedan, we automatically know it is neither a sports car nor a family van. Similarly, if we know it's a sports car, we can infer that it's not a sedan or a family van. Finally, if it's neither a sedan nor a sports car, we know it must be a family van. This means we can express the same information with just two variables instead of three. Including all three variables would make the regression model overdetermined. Okay, but don't worry, if you're using DataTab, it will automatically create the dummy variables for you. For example, if we select fuel consumption as the dependent variable and horsepower and vehicle type as the independent variables, we can then see the three categories here and can select which one to use as the reference category. For example, if we choose sedan as the reference, dummy variables will be created for sports car and family van. When we examine the results, we will see the two variables, vehicle type sports car and vehicle type family van, along with horsepower. Now that we have a solid understanding of regression analysis, including simple linear regression and multiple linear regression, we are ready to move forward. In the next video, we'll explore logistic regression in detail. Thank you for watching and see you there shortly.